All right, everybody, let's wrap up our discussion of the one-way ANOVA by applying it in hypothesis testing. So remember, we have our general question. Does feedback have an effect on self-esteem? And our research question gets more precise. We're really asking, is there a significant difference between the average self-esteem scores for positive, negative, or no feedback? Here we have the same 7 steps that we have been working with since chi-square. Everything, the logic and the flow of it stays the same. What changes is how you state your hypotheses, how you do your calculation, and where you find your crit. But steps 5 through 7 are exactly the same. Do your comparison, make a decision, state your conclusions. So let's start with step 1, which we already did on our last video. We have our variables. We have our independent variable feedback, which is categorical. We got positive, negative, and no feedback. 3 groups there. Remember, because an ANOVA has to have 3 or more groups in the independent variable. We want to know, is there a difference between self-esteem, which is our dependent variable, it's continuous, so we calculate an average from a scale of 1 to 10. Is there a difference in the self-esteem score between the groups of our independent variable? Now, when you're writing your hypotheses for the second step, remember that ANOVA is an omnibus. So it's not worried about 1 or 2 tails. It's not asking where the specific difference is. It's always going to ask just, is there a difference? So the question will be non-directional. The hypotheses will also be non-directional. So the alternative just says yes to the question. You can just copy paste the question and just change the beginning. Is there a significant difference between so on and so forth? The alternative says yes, there is a difference. There is a significant difference. Essentially, what the alternative is saying is that sample 1 mean and 2 mean and 3 mean will be different from each other. The difference will be somewhere in there. And you just take that sentence for the alternative, copy paste it for the null, and you get there is no significant difference, so on and so forth. The null is essentially saying that all the sample means will be equal. There will be no difference between them. Okay, so let's get into actually doing our full hypothesis testing here. So remember, we have the same scenario we worked with last time, 15 people, 5 in each group. They do an assignment, they get feedback, kind of feedback depending on what group they're in, and then they do a self-esteem questionnaire at the end so we can see how they feel about themselves. Okay. Now, the research question, as we already stated, we have our variables, hypotheses abbreviated here for the sake of space, and then we have our F-score that we learned how to calculate last time. Now, the question is, as it always is, how likely were we to find this difference between the average self-esteem scores of positive, negative, and no feedback? Was it likely for us to find these differences, assuming there is no difference between the groups? Or was it unlikely for us to find it? So remember, we need to find the probability of our score. So we need to find the probability of F. And if the probability is less than 0.05, then finding the difference that we found between our groups is considered unlikely. And the way we do this is by comparing our F score to the F critical score, which we're going to get from the F distribution on the F table, which is in your critical scores PDF. Hope you have that in front of you. Find the F scores distribution table, critical scores table, and have that in front of you because I'm going to walk you through how to read that table. It is different than the T table. Okay. Now, just to reiterate, if the calculated score goes past the critical score, it has a probability of less than 0.05. If it's before, it has a probability greater than 0.05. So let's look at how we read this table. So what you're going to see in the table is you're going to see something called the numerator and the denominator. That's referring to the ratio. The numerator is the one on top, that's the between. The denominator is what goes on the bottom of the fraction, that is within. So you're going to need your DF between and your DF within. You're going to need both of those degrees of freedom in order to find your critical score. Okay. So degrees of freedom between will be the numerator. That's going to help you identify your column. Okay. Your column. So let's say that your degrees of freedom between was 2. Well, you would isolate the 2 column. Now use your degrees of freedom within to find the row section. Notice how for each degree of freedom, there's like 3 rows that go with it. So 1 has its row and then the 2 rows below it. Then you have 2 and the 2 rows below it and so on and so forth. So let's say the degrees of freedom within was 3. We're going to isolate the group of 3 there, the 3 group rows. then the alpha levy tells you the specific row to look at within that row group. So our alpha level is 0.05, so we're going to look at 0.05, and then you take the intersection of that row with the column, and then you get your critical score. So if we had degrees of freedom between 2 and within being 3, alpha 0.05, the intersection of those is a crit score of 9.55. And that is how you would find your critical score. Now remember, if you get a degrees of freedom that is not listed on the table, the rule is to round down to the next lowest number, no matter how big it is. What if you get a degrees of freedom that's like, 1,005, and the table only goes up to 6 in the columns, or it only goes up to 100 in the rows? What do? You round down to the next lowest one that's on the table. So if you have 1,000, 100,000, you would round down to 6. For the columns, you would round down to 100 in the rows. You always round down from whatever number you have, you go conservative. So make sure that you keep that in mind, okay? Now, let's go ahead and try to find our critical score. Our critical score. Oh, okay, yeah. So we have the degrees of freedom here, 2 and 12. So go ahead and find that in the critical scores table, and then continue on so you can see if you got the right one. Now, the critical score that you should have gotten is a crit score of 3.89. Okay, this is an example of the F-score distribution. As you can see, it is positively skewed, very much like the chi-square distribution. So 3.89 is there towards kind of the tail area. Now, does our calculated score goes past the crit score? Yes, it does. It does go past, quite far past. So we know that it has a probability much lower than the probability of the crit score, which is 0.05. So we know that our calculated score has a probability less than 0.05, probably very less than 0.05, which means that it was unlikely for us to find the difference between our group means, assuming that we shouldn't have found a difference, assuming that there is no difference between the group means. That's evidence against the null, so we're going to reject it, and we'll accept the alternative as our conclusion, and we restate the alternative hypothesis as our research conclusion. Now what you need to do is take that sentence, put it back into the language of the general question, and it would sound something like this. Feedback has an effect on self-esteem. There you go. That's your general conclusion. Now lastly, just like with the independent and paired samples t-test, we can use bar graphs to visually show what's going on with our numbers even before we look at them. And you can see here that there is a noticeable difference between our group means. In fact, the positive group has a much higher self-esteem rating compared to negative and none. Negative and none are almost the same. Positive is much higher. Maybe the difference is specifically between positive and the other two groups. But again, post-hoc tests would tell us that, but we're not going to do that here. But visually, you can see that there seems to be a difference between the group means. And the bigger the difference between these bars, maybe indicating that there is a significant difference between our groups. And that is how you do the one-way ANOVA in regards to hypothesis testing.